So like Chuck said, I'm more of sort of a general purpose applied statistician, big data sets person, although I'm not going to get into big data sets issues at all in this talk. I have a fair amount of experience over the years in genomics and genetics, but basically zero experience in metabolomics. So I'll try to make analogies, and I think I understand what the analogies are, but don't expect any like real deep specifics when it comes to the issues that may be very specific to metabolomics, because I just don't have background in that area. And I wasn't exactly sure about, well, actually, let me mention one thing first. So my other academic home at the University of Michigan is CSCAR, Center for Statistical Consultation and Research. I think most of you are internal, is that right? Just mostly in UM people? Okay. So if you haven't heard about CSCAR, I just want to make a plug for it. CSCAR is a statistical consulting operation over in the Rackham building, which is open to all UM researchers. And we work with people on all kinds of issues relating to data analysis and study design, statistical software, data management, and data mining and things like that. So if you have data and you have needs to talk to a statistician, a professional statistician, we're there. You can access us for free. Just go to our website and you'll get information about how to make an appointment with us. In terms of what I decided to talk about today, I was invited just to recycle a talk that I gave a year ago at a nephrology conference. I decided not to do that because I was very specialized for one of my graduate students' research projects. I just went back and I pulled some material together that I had that's very basic, and hopefully not too basic, going back to kind of the foundations of statistics and inference and how you deal with basic statistical testing issues that come up in a large-scale screening type of setting, which is common, of course, in all areas of genomics, including, I'm sure, in metabolomics. So some of this, I hope, won't just be like a canned sort of intro stat review. I'm trying to connect it a little bit to metabolomics. Please ask questions. And I guess the reason I thought it was useful to go back to these foundational sorts of questions was that even though they're basic, and many of you have probably seen them before, I find them endlessly fascinating, even decades after starting to think about this area. And they're also sort of endlessly confusing. And there are some issues like multiple testing that I think you can spend your whole life and not really totally wrap your head around. Can everybody hear me? Okay, great. Okay, so I don't want to pretend that there's some kind of recipe or canned sort of role for statistics in any kind of research, genomics or otherwise. But broadly speaking, I think especially in sort of a high throughput molecular biology sort of context, statistics has certain types of roles that it tends to play over and over again. And I'm going to focus on a couple of these in the middle, not necessarily the first one and the last one, but at the level of technology, and I know there are people here like Maureen and so on who are experts in this. You can use statistics to sort of understand the operating characteristics of assays. That's not really my thing. I'm not going to talk about that today. It's a very important role of statistics in high throughput molecular research. What I'm going to focus on today are the middle two, which is the discovery and validation of what I'll call potentially interesting or useful associations, patterns, relationships, whatever you want to call them, in large data sets, for example, in metabolomics data sets. And the second and third point here, there's really not a bright line between them. It's not like you discover something and then you validate it. It's really there's a process of building evidence towards ultimately believing something. And that it begins with just sort of something that's more or less like a fishing expedition, followed by sort of different sorts of statistical refinements, followed by a collection of additional data and supporting evidence until finally you start to believe it. And then finally, the last point, which is something I'm very interested in and comes up all the time in my work, but just won't really be able to get into today, is once you've discovered all these sort of building blocks of information in a large data set, whether it's metabolomics or what have you, then you kind of want to integrate and put that information together to do something. And for me, being often more at the clinical end of the spectrum, that often amounts to taking a bunch of biomarkers and putting them together and figuring out what you can do usefully with a biomarker panel in terms of making some sort of prediction or providing some sort of decision support to clinicians. And there are very interesting statistical issues that come up there because you have to accept the fact that a lot of individual pieces of information, when brought together, don't always kind of come together in an additive way. So there's often a lot of redundant information as well as what we would call synergistic information, in which the whole can be either less or more than the sum of the parts. And that's, to me, a fascinating aspect of this area, but it's not something, like I said, that I felt that I could do justice to in the amount of time I have today. So I more or less left that out, and I'm going to focus on the middle 2 points. So please interrupt me and ask questions if anything I say is unclear, if you have a question. So not to sort of be too basic about it, but the question that comes up, in my view, most often, and I often encounter this starting maybe 12, 15 years ago in the world of analysis of gene expression data, is that you have a 2-group comparison, 2 people with, say, advanced disease and indolent disease or what have you, And you measure the expression of something, the expression of a gene or the abundance of a metabolite or the abundance of a protein, what have you. And the question becomes, is there what you call differential expression or differential abundance? So in other words, is there a difference in the levels of that molecule in the two samples derived from two, or the two sets of samples derived from two different types of, say, individual, animal, person, whatever. And you see something that looks sort of potentially intriguing but not particularly convincing on the other hand, and the question that comes up for statistical purposes is this a real difference, whatever it means to be real? And we'll talk about that from a little bit more foundational perspective in a few minutes. So this one's, pretty weak, and you might struggle to say anything very convincing about this. There's maybe a bit of evidence that group 2 is higher for this metabolite than group 1, but it's obviously not particularly strong. And arguably, this is maybe a little bit stronger. We have situations where instead of looking at the relationship between two groups, you have a continuous outcome, like canonically it could be something like blood sugar or blood pressure or what have you. And the question becomes, is a certain, say, metabolite or expression level of a certain gene correlated with this continuous outcome? So is there a trend there? You like to see it, but is it real? Whatever real means. As I said, I'll get to that in a minute. Maybe you have a more complicated type of data in which you have subgroups, or you have a mixed population of individuals with different backgrounds or different covariates. And the question becomes, is there a relationship between the outcome and the metabolite in some sense when you control or adjust for other potential known confounders? So this is sort of the basic question that I'm going to pretty much exclusively focus on today in my 30 minutes or so. How do we assess whether differences like this are real, and what does it even mean for them to be real? And actually, realistically, we're not just talking about a situation where you're presented with a single metabolite, and the question becomes, is this metabolite's abundance associated with an outcome or trait? What really happens, as you all know, is that you measure a large number of, say, metabolites, not just 25, maybe 25,000, and each one of them has some evidence or other of being differentially expressed between two groups or associated with some outcome. And sometimes every time I generate these slides, this programmatically gets updated, so I don't know where the hits are, but whoops, that's not the pointer. Sometimes there's maybe a little bit of evidence, sometimes there may be more of an evidence, but what additional factors do you have to consider when you're looking for sort of the strongest evidence in a pool of 25,000 tested candidates, potentially for which you had no a priori hypothesis about which ones might be interesting, versus a situation where you're presented with one or two potentially previously validated metabolites that you then want to confirm in your population or confirm in a slightly different treatment context. That's more of what we call a confirmatory analysis, whereas what I think is more the focus here is the exploratory context, where you're doing some sort of high throughput, large-scale screen, and you don't have strong a priori hypotheses about which markers are potentially important. And so what you end up doing, naturally enough, is just sort of scanning through the output and looking for the strongest signals. And then the statistical questions actually become quite complicated quite quickly as to what's the strongest out of 25,000 tests is really strong enough to believe. Okay? So this is where I get a little bit didactic, so forgive me. But just to sort of set the stage for where how statisticians think about these issues, because if you don't have a solid foundation, these questions are almost unanswerable or nonsensical even. I'm sure you all know that statistical thinking, statistical inference, all takes place in this context where we think about the difference between the population and the sample, the population being the sort of abstract universe of data that we could potentially observe, and the sample being the concrete data that you actually did observe. We can say anything you want about the sample, and you don't need to do inference, right? There's no question that the mean of this sample is higher than the mean of that sample, and the median of group 2 is higher than the median of group 1. There's no question, there's no statistics that needs to be done there. The real question is whether or not the mean of the population that group 2 was sampled from is higher than the mean of the population from which group 2 was sampled. That's the real question, and that's obviously much harder because it asks a question about things we can't actually see. So we have to make assumptions, and using those assumptions, hopefully come up with some evidence that would suggest that we would in fact be likely to see the same pattern if we reproduced our very expensive and time-consuming experiment and generated an independent but equivalent set of data, right? So that's what this framework of the sample and the population allows us to do. It allows us to put the question of whether or not a difference is real on a solid sort of foundation, and then apply mathematical tools that I won't really get into today to be able to state rigorously what we know and what we don't know or can't know about the potential for a given relationship that we observe in a particular set of data to generalize to either a new set of data drawn from the same population or to reflect that abstract population entity itself. There's a classical way of thinking about these issues, and then there's a lot of misgivings and concern about those classical approaches, especially within the community of statisticians that you may not even intersect with very much. So I'm going to present the classical way of thinking about these things, and then later on I'll tell you a little bit about why people are somewhat troubled by the classical way of doing this and why in the world of statistical research people are looking for alternatives, although not necessarily finding an obvious candidate for a replacement to the classical paradigm as of yet. In the classical paradigm, we tend to think about these comparison-type issues from the perspective of there being sort of two separate things going on at the same time. There's something we call the effect size, and there's something we call the significance level. And these are important to distinguish and often not well distinguished by people. The effect size is basically a statement about the magnitude of an effect. So how big is the difference between, say, I'm going to generally focus on the two-group comparison because it's the most basic setting, and it's easy to generalize to any other kind of setting, like the correlational type of setting, which I showed in the scatter plot earlier. So in the two-group setting, the effect size is basically a statement about how different something is between two groups. And most concretely, you could say, like, how different is the mean expression level or the mean abundance of a certain metabolite in one group versus another? How big is that difference in either absolute units, whatever the units of the assay are, or in some kind of more statistical units, like standard deviation units, right? And actually, in the early days of genomics, the people looking at microarrays only looked at fold changes, which basically is the canonical measure of effect size. So they basically said if something's twofold up, it's real. If it's not twofold up, it's not real. That's the most basic way to think about effect sizes in genomic studies. And it didn't take long before people realized that that in and of itself wasn't sufficient, because being twofold up in an experiment with a sample size of 4 doesn't necessarily mean the same thing as being twofold up as in a sample size of 100. And the missing piece there is this notion of significance level, and this is where all the concern comes in within the statistical community. Is I think everybody accepts that we're thinking about effect sizes the right way. That's a pretty basic and concrete concept, but there's a lot of concern within the community of statisticians as to whether or not we're really thinking about significance levels right, even 80 years after the concept was more or less introduced by Fisher and some of the other founding statisticians of the modern era. But be that as it may, we're kind of still stuck with what we have. So the notion of a significance level in the classical sense, and I won't really define it here mathematically, except to say that it has something to do with this counterfactual type of thinking, is that is the effect size big enough that we should be surprised by it, in the sense that if the true effect size were 0, would we be very likely to observe an effect as large as the one that we actually observe? So I'm just saying that almost sounds ridiculous. Like, why do you have to use such convoluted language to get at such what seems to be such a simple, obvious concept? And in fact, it's turned out to be remarkably difficult to come up with a more useful way to think about significance. So, like I said, that's basically the way all practice in these areas is currently done, for better or for worse. So let's go back to the notion of effect size for a minute. Like I said, you can think about effect size in raw units, or you can think about it more in statistical units. But for me, it's almost always more useful to think about it in terms of statistical units, unless you have a very solid handle on the units of your assay, molecules per mole or whatever your units are. You're almost always going to be wanting to thinking about it in statistical units. So the notion of an effect size in statistical units is basically simply a question as to how far is the mean of the population shifted away from some reference point in standard deviation units. Right? And I think basically we all have some kind of handle of what a standard deviation is. Standard deviation is basically sort of halfway across the middle of the range, halfway up the histogram or density function. So this is on this graph, this interval here represents one standard deviation. Like you see, it's about halfway across the range in the middle of halfway up the density. It depends on the details here, but what the distribution is, but it's roughly in that range. So if you have an effect size of 0, of course, that means there's no effect. So the reference point, the mean of the population sits right on top of the reference point. An effect size of 0.1, which, believe it or not, is big in the world of genetics, is something like this. It's almost visually imperceptible. It means that the distribution is shifted ever so slightly off of some reference point. And whether or not that's biologically meaningful is a separate question, but that's an effect size of 0.1, and it always will become significant if the sample size is large enough. This is one of what people call the paradox of classical inference, which is any non-zero effect size, no matter how small, will always become significant if your sample size is large enough. And in genetics, and this isn't a genetics workshop, I realize, but in genetics, as many of you may know, people have huge sample sizes, in the tens of thousands often, and so effect sizes like this become significant, and a lot of what people trumpet as the outcome of different so-called GWAS studies is associations of that magnitude. I don't really know in metabolomics. I do know in other areas of sort of downstream from the genetics, molecular biology, like gene expression and so on, this is not considered to be a particularly interesting effect size given the smallness of the magnitude. And I assume that in metabolomics that is also the case. Effect sizes of 0.5 are starting to get interesting, and effect sizes of 1 are actually quite large. So that's the notion of effect size. Now, what I just showed you on the last slide is really a little bit of an artificial situation, because we often are not doing what's called a one-sample analysis where we compare a single population to a reference point, because we often don't have a reference point or a meaningful reference point to compare to. Much more often we're doing something that's more comparative. So we have two populations that we're comparing to each other. But the same logic basically applies, is that the two populations have mean values, and you don't have to compare the means. Of course, there's a whole branch of statistics built on comparing quantiles or comparing other moments or other summaries of distributions, but the same basic concepts apply as here. So I'm just going to focus on the setting where you're comparing means. The means can be shifted by half of a standard deviation unit, one standard deviation unit, and so on. And again, this you can hardly see, but there are actually two density curves there that are offset by a trivial amount. But this, again, is a small effect size that would still become significant as the sample size grows, but potentially not very biologically significant, but statistically significant. And then a sample size, effect size of 0.5 and is actually pretty interesting, and 1 and larger are huge and almost never seen. Minor technical detail is that the two populations being compared obviously don't necessarily have the same degree of within population variation. So the stereotypical schematic plots I showed you on the last two slides had equal variance. They don't have to have equal variance. So here's a situation where you're comparing a population with a large mean to a population with a small mean. There are ways to handle that. I think you all know. I don't want to dwell on that. So again, as I said earlier, the limitation of taking only in a perspective where you only look at effect sizes is that what we actually do in practice is we estimate the effect sizes from data. If someone just told you what the effect size was, then it actually would be sufficient just to look at the effect size and we could just end right there. But of course, what really happens is we have a rather limited amount of data, and then we estimate the effect size from our data. And even if the effect size in the population is 0 or extremely small, you still have some chance of estimating the effect size to be larger than 0. So in some sense, the magnitude of the effect size is always biased upward. It's always biased away from 0. The magnitude of the effect size is always biased in that way. And so one way to make this concrete is to think about what's the chance of observing an effect size of, say, 0.1 or larger, or 0.25 or larger, or 0.5 or larger when the true effect size is 0. So in other words, what's the chances of overstating the effect size by a certain amount because we're estimating it rather than observing it exactly? And that, of course, depends on the sample size. As everyone knows, the more data you have, the less likely you are to make a gross mischaracterization of the population based on your sample. And the forms of these curves are given by mathematics that I won't get into now, very basic mathematics. But just a couple comments. One, it doesn't drop as fast as you might hope. Especially once the sample size passes a certain point, the incremental gain, and so this is sort of a reflection of power, the incremental gain in power is small as the sample size grows. And the chances of making a small overstatement of the effect size are actually very large, approaching 50% for smaller sample sizes. But fortunately, the chances of making a large overstatement of the effect size are rather small. Right? But as I've said before, the premise of statistics, as inherited from the classical era, is not just that we want to estimate the effect size accurately, but we put a special emphasis on this question: is the effect size 0 versus non-zero? No matter how small it is, if it's not 0, it's not 0 in that framework. And that's, again, one of the concerns that a lot of us have as to whether that's even the right way to think about things. But that is the way it's thought about. I won't really belabor the mathematics of this so much. We do have this concept of a standard error, which I'm sure you're all familiar with, but it always is useful, I think, to review what it means. So roughly speaking, the standard error is the average error you make when estimating something with your data. And so it depends on the design of the study, and it depends on the nature of the thing you're estimating. So it depends on the design of the study, because the more powerful your study is, usually that's due to having a larger sample size, but it can be due to other aspects of the study design that improve the power, the lower the standard error will be. And the more sort of noisy, intrinsically noisy the thing you're aiming for is, the larger the standard error will be. So you don't normally have any control over the latter. If you're trying to estimate something that's intrinsically noisy, intrinsically variable, that just is, you can't take that away unless there's sort of extraneous factors that can be controlled or something like that. But often that's just a physical reality that you can't eliminate. But you can, of course, modify the study design. And so that's why study design, I know it's on the agenda for multiple speakers in this two-day workshop. Study design is so important, because if you start off with a inadequate study design, you're going to have a large standard error, and once you've got the data in hand, there's nothing you can do to make that go away. Instead of going through the formulas, let me talk about standard errors from the perspective of this graph. And again, we're talking here about this canonical setting in which you're comparing two populations based on samples drawn from each of the two populations. And this is now a situation where we can look at the standard error versus the combined sample size of the two samples. If it's a two-sample comparison, I threw a one-sample comparison on here too, just as a reference point. And again, what we see is the standard error. This is not quite the same as the plot we saw a minute ago, but this is a plot of the standard error against the combined sample size. And of course, again, what happens is that the standard error drops as the sample size increases. This is roughly like this 1 over root n type of relationship that you see all the time in standard error. So if you want to cut the standard error in half, you have to increase the sample size by a factor of 4. It's kind of a frustrating but unavoidable reality. A one-sample comparison, like I said, we don't often encounter because we're not usually comparing against a fixed reference point. That's shown in the blue curve. And so for a given total sample size, a one-sample situation is best. The way to think about that is that a one-sample situation is really like a two-sample problem in which you had an infinite sample size to estimate the thing you're comparing to. Right, so there's no uncertainty in the target value that you're comparing to or the reference value you're comparing to. More realistically, you have to estimate both the reference point and the point that you're comparing to the reference point. So if you think of the reference point as being like the expression of a metabolite in a normal population, a healthy population, then you have to estimate that as well as estimating the mean expression of that metabolite or abundance of that metabolite in the disease group. So there's uncertainty in both estimands, and the uncertainty in those two estimands combines to create more aggregate uncertainty than you would have if somehow you were magically able to know what the control value was. And the main point I want to make here is just from the study design perspective, as often comes up in sort of basic discussions about study design, is, do I have the same number of controls as I have if it's treatment or disease or whatever the non-control group is. So what we see here is if you have a 1-to-1 ratio of controls to non-controls, then you come pretty close to approximating the situation with the one-sample design in terms of the standard error being only slightly higher. But if you have a skew in the sense that you have, say, 4 controls for every non-control, or equally so the other way around, then the standard error shoots up. And basically what you're seeing here is the fact that the standard error is dominated by whatever thing you know the least about. So if one of the other groups you don't know too much about, then there's huge uncertainty in that thing, that estimand, and that dominates the overall uncertainty of the analysis. Now this, I have to qualify this, is for teaching purposes. The reality is often a little bit more complex, because if the intrinsic variability in either the control group or the non-control group is higher, then it's not necessarily the case that you are best off doing a 1-to-1 match of controls to non-controls. So if you knew that your disease population, for whatever reason, in terms of the abundance of a certain metabolite, was more variable, so that metabolite's levels are more well controlled in, say, healthy people than people with a disease, then you would actually want to oversample disease beyond a 1-to-1 ratio to account for the fact that it's sort of intrinsically more variable. And there's very simple formulas that will tell you exactly how much oversampling you should do. So conceptually, I think it makes sense, and the formulas are out there to be found. But the main point is that you often will not find that there's massive, what we call heteroscedasticity, or unequal variances between populations in this sort of two-group setting. Or if there is, you don't know about it ahead of time, so there's no way you can build it into your design. So 1-to-1 isn't necessarily such a bad place to start. I want to talk now about a concept called a z-score. So I know that for better or for worse, most of statisticians think for worse, the statistical practice in these fields are dominated by p-values. And we sort of hate p-values for a lot of reasons that I won't get into here. But there's a related concept. I mean, I won't even get into it. But there's a related concept called a z-score that we're a little bit more comfortable with. So I want to talk about z-scores a little bit, to kind of give a plug for z-scores. And you won't see the word p-value mentioned anywhere else in this talk. So we just talked about standard errors, and we said again that a standard error is simply the average estimation error you make when estimating a given unknown target with a given amount of data that came from a given design. So the ratio between the estimand and its standard error is what's called the z-score. At least in the one sample context, or in the most basic one sample context. And this can be generalized to other settings. And so basically the idea is by taking the ratios, what you're saying is how far from the most uninteresting thing is my observed effect in terms of multiples of the expected error. Right? So a z-score of 1 means that, yes, my estimand did not fall exactly on top of the least interesting possible value, what you sometimes call the null hypothesis, although that's another term that we don't like to use too much. So it didn't fall exactly on top of it, but if the z-score is 1, it says, well, it only fell one expected error away from it. So in a sense, it fell exactly where you would expect it to fall. Exactly one error away is exactly where you would expect it to fall. So a z-score of 1, you can see very clearly, is not a very interesting outcome, or at least it's very consistent with the so-called null hypothesis. A z-score of 2 means that the effect was, in a sense, twice as big as could be explained by pure error. Now, depending on the statistical properties of that error distribution, having an error that's twice as big as average may not be so unusual, or it may be quite unusual. But at least it's not the most common thing. It's not as common as an error multiplier of 1 or a z-score of 1, which is exactly what's expected. And so a z-score of, say, 10 means that your effect is sort of 10 times bigger than could be expected or to be explained by pure estimation errors. So that's clearly a pretty big effect. It happens that, I think I have this on the next slide. Well, okay. Very briefly, you can generalize this concept of a z-score away from the one sample setting to the two sample setting, which again is what's much more likely to occur in practice. Okay. So the z-score gets back to this notion of the significance level. It's telling us something about kind of how surprised we are to see the effects that we saw. Again, if the z-score is 2, it means that the effect is twice as big as one would expect from error and from estimation error. And it turns out that z2 threshold is significant. Well, I shouldn't say significant. It's a nice reference point, not only because 2 is just sort of a nice round number, but also because it corresponds to this thing, p-value equals 0.05, which is sort of canonically used in all research, in all areas. So it turns out that if none of the data are normal, there's a lot of misconceptions about the roles of normality and all this. Normality is much less important than many people think it is. But if certain sort of mathematical properties hold that lead to the averages behaving as if they're normal, which actually is quite a broad set of scenarios, then a z-score of 2 corresponds to a p-value of 0.05. But I'd much rather think about it as a z-score of 2 than a p-value of 0.05. I'm just saying that the effect size is twice as big as I would have expected to be accounted for by error. So that's a bit of a primer on z-scores if you haven't seen that concept before. This in and of itself probably doesn't make you too excited about z-scores, but as you move, and we won't have time to do this, but as you move into more subtle forms of inference, then focusing on z-scores rather than p-values continues to have payoffs in terms of interpretation and ease of calculation and other things. I do want to point out here that once you start calibrating your z-scores, what it means to calibrate a z-score is to turn it away from just a pure ratio, which is correct by definition, because all it is just a statement about a ratio, and turn it into a probability. That's calibration. And that's where things start to get really complicated, and conceptual mistakes can be made very easily. So this idea that a z of 2 corresponds to a p-value of 0.05 only holds really in a very artificial situation when you're performing a single hypothesis test, which you've pre-specified before you even collect the data, and you promise not to look at your data or ask any other questions of your data than that one single pre-specified test. Once you move beyond that artificial framework that's never really holds in practice, then your z-score is still a z-score, but your p-value is no longer a p-value. And that's, I guess, maybe the easiest way to say why do I like to at least start off by thinking in terms of z-scores and only convert to p-values when I have to. So that's the calibration question. How do you convert a z-score to a p-value? And that's very dependent on the context of how you're analyzing the data. Question here.
Is there some publications that use z-score instead of p-value?
All over the place. I mean, I always try, and only if when stuff I'm involved with, and always try to, and only if referees ask me to convert things to p-values, I'll convert to p-values. Sometimes referees just insist, and I do it. It's not that controversial. I'm not saying here that's anything that's my own sort of, personal vendetta against p-values or anything like that. And broadly speaking, applied statisticians in many fields, far away from biology as well as within biology and medical science, use z-scores. Sometimes at the end for presentation, you convert to p-values for presentation purposes. I'm just trying to encourage people to open up to thinking about z-scores during the analytic process. And then if you need to convert to p-values at the end, that's fine. I didn't catch your first.
If the result is obvious, you don't need to...
Well, that's exactly true. So that's a really good point about statistics, very broadly defined, is that some effects are obvious. If the z-score is 10, the p-value has so many zeros in front of it, it doesn't matter what you call it or what sort of framework you use. And so we end up spending most of our time operating in that realm where, because powerful study designs are expensive, people will always go to the bare minimum in terms of power for their study, which means that the effects are realistic to find, like a twofold effect, is always going to be just at the borderline of being detectable. People rarely overpower their design so that even real effects rarely poke out above the noise, the estimation noise to that degree. But if for whatever reason the question you're asking is easy from the perspective of the design, then yes, there's no controversy at all. Okay, let's see what I have next. So this is sort of a separate issue, but I just wanted to point this out too, is that one of the most interesting contributions, I think, or most useful contributions of statistics to applied research involving data is the idea that you can adjust or control for what you might call confounders or other factors analytically if you can't control for them in the experimental collection process. So I know that I've seen the word confounder on the agenda for other talks, and obviously you all know what confounders are. To put this in sort of a slightly different language, what we would say in sort of statistical language here is that we're talking about conditional versus marginal association. So marginal association would be an association between, say, the expression of a metabolite and some group identity or outcome that's unconditional or uncontrolled for anything that wasn't controlled for in the data collection itself. Whereas a conditional association is some sort of a statistical attempt to control for something like, say, gender or age or whatever other potential confounding factor you have after the fact. It has to be something you collect data on, of course. You can't, using the techniques that we're most familiar with at least, you can't control for something you don't observe. But you can control for something that you didn't control in the experiment. And so this, I think, I don't want to diminish the contribution of statistics to research, because if it's all just about sort of box plots and that sort of stuff and simple mean comparisons, then it's not clear that we really deserve to have our own field. So it would just be sort of a minor little extension of some mathematical thinking. But once you start thinking about conditioning and adjusting and so on, then statistics can become quite deep and subtle quite quickly. For example, here's a situation where the differential effect actually becomes stronger when you control. So I guess one of the points I want to make is that people often think of statistical adjustments as taking away from your effect. So you get the canonical situation is someone gets excited, they say, I found an effect, this metabolite is expressed in a manner that's associated with some trait, and then someone says, well, you need to adjust for this and you need to adjust for that. And people expect that, well, every time you adjust for something, it's going to make the effect weaker. It's not actually true. Adjustment can make the effect stronger as well as weaker. Confounding typically makes effects weaker because you're removing an effect that creates an artificial difference. But in general, it can go either way. Here's a situation actually where the effect becomes stronger when you control. So if I didn't have the color here, I'm not sure you would say that these two populations, the populations underlying these two samples are different. You may. I mean, this one looks a little bit higher than that one, but it's not that convincing without the colors. But the colors, say, could represent gender or something like that. And once you know that the orange samples, say, are females and the purple samples are males, you see a very consistent pattern in which the females are going up and the males are going up. But because I forgot what I said was which color was which, but there are more purples over here and the purples are higher, and there are more oranges over here and the oranges are lower, at the margin level the effect is much weaker. So this is in a situation, I should have calculated a p-value just so you could see how how big of an effect there is when you control versus not control. But this is a situation where it probably would not be a significant difference without controlling, but it would be an extremely significant difference after controlling. So, of course, the opposite can happen, where you have a situation here where, say, males have a higher expression than females, and there are more males in group 2, and so you see something as a potential group-related difference when, in fact, it's a gender-related difference, which may or may not be interesting, but the fact is that calling it a group difference is slightly misleading. So this is sort of the canonical confounding situation, but the thing I showed on the last slide shows that it can go the other way as well. So I've alluded to the notion of multiple testing a few times. So I think in the genomics world, somehow it seems like 98% of the time statisticians are involved with issues relating to multiple testing, kind of for good reason, although sometimes we feel like we're like playing the role of the multiple testing police, whereas we go around and tell people that the results that they calculate don't really mean what they say they mean. And in that case, you're almost always throwing cold water on something, because correcting for multiple testing is never going to make the story stronger. It's always going to make the story weaker. It may make it correctly weaker, but it's not never going to make, so it's not going to make people happy, basically. So I hate being the multiple testing police. So I try to actually avoid being the person who's like always beating this dead horse, so to speak. But I can't, in this context, not mention it, because it's incredibly important. It's also incredibly subtle, which is, I think, one of the reasons why some sort of practitioners, or experimentalists, just, in a sense, refuse to accept that they have to deal with this multiple testing issue, because it's sort of a, what's the right word? It's sort of paradoxical in some ways that you even have to do this, and yet we pretty much all agree that you do. So what is this all about? So basically what it means is that if you have a, for lack of a better word, fishing expedition type of study design, where you're measuring a large number of things, metabolites say, and then you apply some sort of summary statistic or descriptive statistic to the data to quantify the extent to which each one of those things is potentially differentially abundant between groups, maybe after controlling for other factors, maybe not. And then you force rank the metabolites, say, from the most potentially different to the least potentially different, and then you jump on the top one and say, this thing individually has, say, a p-value 0.0 whatever, as if it was the only thing that I tested. Clearly that p-value doesn't mean what, hopefully it's clear that p-value doesn't mean what people want it to mean. Right? And a p-value of 0.05 in this context really doesn't mean anything. So a property of p-values is that they are what we say is uniformly distributed under the null, which means that if there's nothing going on, if the two groups that you're comparing are different in every possible way with respect to every possible metabolite or gene or whatever, then the p-values will be uniformly distributed, which means half of the p-values will be less than 0.5, 10% of the p-values will be less than 0.1, 5% of the p-values will be less than 0.05, 1% of the p-values will be less than 0.01. So you can't really use 0.05 as a reference point. If you test, say, 10,000 candidates, you expect 5% of them to have a p-value of less than 0.05, even if every single one of them, in fact, has no difference at all. So unless you get many more p-values, not what we call nominal p-values, because p and p-value, of course, stands for probability, and they're not probabilities in this multiple testing context. So I guess if you want to call them p-values, it's fine, but don't interpret them as probabilities. So you have to get more than 5% of your, quote, p-values to be less than 0.05. And I said before, you can do all this in the language of z-scores as well. And so sometimes people will get, say, let's say they do 100 tests, so we make the math easy, and they get exactly 5 below 0.05. That's not really any evidence that there's anything going on, because you would expect to get exactly 5 below 0.05 in that setting. And that concept of the number of things that fall below in p-value terms or above in evidence terms a particular threshold, that's called the false positive rate. So that's basically the proportion of all tested entities, tested candidates, that are truly null, truly have no difference between the compared populations, but that have apparent evidence for being differentially abundant at some level. So that's the rate of false positives. If you use nominal p-values to make your decisions, then your false positive rate will be 5%. That means 5% of everything that you produce will be false. The more rigorous way to do this, maybe even too rigorous, I would even admit, is this notion of a family-wise error rate. So the family-wise error rate is a different probability. It's the probability that anything you're claiming in your entire analysis of a given data set is false, right? So if you want to bound your family-wise error rate at 0.05, it means you want to guarantee that sort of 95% of the time you will never make any false statements about a given data set. And that's probably too conservative in the other direction, right? You don't necessarily want 5% of everything you test to produce a false positive, but you also don't necessarily want to have all of the analyses you produce have no errors. I mean, we have to accept that if there's uncertainty in our data, if we insist on not making any errors, then the only way to guarantee not making any errors is to not say anything at all. Okay. So the way to guarantee you get the family-wise error rate bounded is through this technique called the Bonferroni adjustment, which you probably all heard about before. And basically, it's extremely easy to apply. All it basically asks you to do is to multiply all your p-values by the number of tests. So I have an example here somewhere. Yeah, so if you have a p-value of 0.0005 and you did 100 tests, in other words, if you had 100 candidates, none of them was a priori more favored than another, then you would multiply 0.0005 by 100 and you would get 0.05. So that would pass, so to speak, the Bonferroni test, but just barely. So the nominal p-value has to be very small in order to get just the weakest possible, in the classical setting, the weakest possible evidence for there being differential expression. This is actually what's done by and large, not exclusively, but by and large in genetics, because there's such a bad history of non-replication and dubious findings coming out of GWAS and other large-scale genetic studies that people pretty much came to only accept the most conservative and rigorous possible approach, which basically means in those genetic studies where they're testing, over the whole genome, 10 to the 8 SNPs potentially, is that you have to have a p-value with many, many, many zeros in front of it after the decimal place before you can consider it to be real. So it sounds a little bit odd, but that's the convention. Now, I would accept that in metabolomics, more like genomics and other areas of sort of downstream from the genes, that you don't need to be so conservative. And this notion of a false discovery rate started to become popular within statistics maybe 10, 12 years ago. It actually had been around sort of colloquially for decades, but it became formalized and its properties were studied by some famous statisticians at Stanford and Johns Hopkins about 10 years ago. And it's become a quite useful tool. It's somewhere in between this sort of nominal significance sort of thing where you just do and analyze everything and do your inference as if it was a pre-specified hypothesis, which I think is way too slack in terms of being rigorous, versus this Bonferroni-based family-wise error way of thinking, which is excessively conservative. So intuitively, I think it makes a lot of sense for laboratory scientists. Is you say, I'm going to make a certain number of claims based on this data set, and I want the claims would be anything that I put on a list as being my statement as to what's differentially expressed. And I want to bound the proportion of those claimed claims of differential expression. I want to bound the proportion of those things that are false statements. And you might be comfortable, the 5% no longer has any favored role here. You might be comfortable making 5% false statements. You might be comfortable making 10% false statements. Most people aren't going to be comfortable making 30% false statements, but it's a little bit more individual where you fall there. It doesn't need to be 0.05, but 5% is often used, 10% is also often used, somewhere in the 5 to 10% range, right? So you might produce a list of 150 metabolites from a screening study of some sort, and if that list has the property of having a false discovery rate of say 10%, it means that I shouldn't have done 150. Let's say I did 200. Then that means you are accepting that there's 20 false claims on that list. So 20 of those metabolites are presumably not actually differentially abundant in the groups, but the other 180 are. So you've made a lot of progress. You've discovered a lot of stuff. Of course, you can't tell people which 20 are false and which 180 are real, but many people would be willing to accept a list like that, acknowledging that a few things won't pan out, but most things will. Right? Now, there are a lot of reasons why, and I'll close on this point. There are a lot of reasons why statements like that may actually be slightly over-optimistic, even if you claim that only 20 are false, but potentially more are going to be false. The other thing that will often come up is that even the dichotomy of being false and real purely based on whether the effect size is exactly 0 or not doesn't capture the whole story, because what will often happen is that pretty much everything will generalize, but it will generalize at a smaller effect. Right? So you discover a bunch of stuff and you say, these are all real, and they're all real with an effect size of bigger than 2. And then someone does a follow-up study, and they say, well, yeah, in some sense you were right. 90% of the things you claimed were real also appear to be real to us. But almost everything has a smaller effect in our data than it did in your data. And it's sometimes called the decline effect. And it's been noted a lot in these sorts of areas where there's just a lot of sort of intensive sort of screening through data and mining of data. And effect sizes almost always go down as people investigate more and more closely what's going on. So I'll close on that note. I think the last slide just mentioned some other things that I think are interesting and important that I didn't have a chance to talk about today. So thank you.
Even worthwhile making any statements or conjectures about effect sizes based on preliminary data?
Yeah, so the issue, it's very difficult. People have been looking for a good way to say, so here was the most significant, say, metabolite in my screen. I'm pretty sure it has a real effect, and its estimated effect in my data was, say, it was threefold different between groups. Now, how much do I need to revise that downward to acknowledge the bias that comes from the fact that I picked it off the top of the list? And that turns out to be extremely difficult to do. And so I think the simple answer to your question is that there's no simple formula that you can filter that effect size estimate through to sort of downscale it to reflect the effects of selection. There's a lot of research on it, and there are techniques out there that people have proposed, but I would just say that not any of them has really been convincingly demonstrated to be convincingly useful in a broad range of settings. There's two people in the back.
Kerby?
Yes.
Just take the lead. So, the advantage we have with metabolomics is that there is a lot of relationships between metabolites that you can actually see. Mm-hmm. So let's say you had your 20 metabolites and you figured that 10 or 5 of them are not right. But if 7 of those 20 are related somehow in a pathway, can you just rapidly move to, I'm feeling much better about these? Obviously, intellectually you would be, but then how do you handle that from like maybe a prose or a statistical point of view?
Yeah, so I'm taking sort of an obsessively deconstructivist perspective here. Every molecule is like an atom unto its own self, and all the evidence for the expression of that thing or the differential expression of that thing has to come from the data for that one thing. So as Ala was showing us earlier, there's all kinds of ways to integrate information across different molecules. One of the ways that plays out statistically is that the Bonferroni correction itself becomes conservative precisely because these things are redundant, and you think you're carrying out, say, 10,000 tests, but because of the strong degree of correlation deriving from the network structure, even mathematically, the number of effective tests is much lower. And we have actually some work that I actually kind of like, but no one's ever paid any attention to it, that shows like the sort of effective degrees of freedom, this is in gene expression, of the genes that are interrogated by a microarray, which appears to have sort of like 10,000 different assays on it, but the effective degrees of freedom is like 80. And that just comes from the fact that they just don't move independently. So maybe you only need to do a correction for 80 tests rather than 10,000. But again, this is one of these things like the question about how do you downscale the effect size. And you know that you're being conservative, but it's extremely difficult to know how conservative you're being so as to be able to make adjustments in that way. I think of course, there's all the stuff that Ala talked about, which bridges statistics and then the science. But in terms of actually adjusting the statistics to account for dependence, we know that you should and that it's excessively conservative for that reason. But mechanically, there's not a sort of simple silver bullet that adjusts for that. Okay. Okay.
So one of the important problems we face in metabolomics, and I'm sure it's partly in proteomic data as well, is basically the absence of data in samples. So basically, you have a missing data.
Yeah.
At least in metabolomics, there's part of the problem is also the data extraction capability. The software is not great. But let's assume that it's just not an issue with the software, it's just a real measurement. It's below the level of detection. Can you talk a little bit about how you handle those missing data and imputation of data?
Yeah, the missing data is a fascinating topic, and the University of Michigan is sort of a center of activity for this area because Rod Little, and former chair of our biostatistics department, was sort of one of the fathers of the field of missing data analysis and statistics. Not so much in his case in the genomics realm, but I think he was one of the first people to recognize that missing data is not just a nuisance, but it's actually an area that deserves to become like a formal branch of statistics. and he's thinking more in terms of things like people not responding to telephone surveys and things like that. But I think the influence of his foundational work has percolated through. The tricky thing about this, of course, is we have this notion of informative versus uninformative missingness. If the data is uninformatively missing, which you can think of in some sense as being missing at random, which means someone just went through and randomly deleted data points in your data set, then the methods we use can accommodate that form of missingness, but they only accommodate it in the sense that they give you the right result for that amount of data. They don't sort of make the missing data come back to you, because in a sense you can't in that situation. My thinking in proteomics, and again I have no reference point for this in terms of metabolomics, is that a lot of times the data are actually missing in an informative way because and we've talked about this recently, but as the abundance goes down, the true abundance goes down, it's more likely to be undetected. And the question is that just a zero? Well, it's not really a zero, but on the other hand, it's not missing at random because the fact that it wasn't observed means it's likely to have a true level that's quite low. And there's a whole, literature in the bioinformatics literature on either imputation or sort of post hoc corrections or various sorts of adjustments that can be made to account for that. So it's an important issue. I don't think there's one. I can think of 3 or 4 techniques that are used, and the simplest one really is just to stick a 0 in there, but that's not really recommended, or to stick something in there. But there are multiple imputation is another idea that came out of the survey sampling literature that's rarely applied in this field, but probably should be. And there are ways to do multiple imputation in a way that acknowledges the fact that the values that are missing aren't just random, they're actually likely to be at the low end of the range. But I think I'll just say that it's an important issue, and you have to account for the fact that it's not missing at random in this field. Yeah?
In the metabolomics data for the normalization, if we do 2 runs means 2 batches, usually we use internal standards for the normalization. But sometimes we feel the internal itself a variation. So in such case, how do we normalize statistically the 2 batches?
Yeah, normalization, batch effects. This is something that we've been having to deal with as long as I've been working in this area. And I don't know what the particulars are of what happens in metabolomics, but in every omics area, you have issues with batching, and there's this idea that you can just normalize away the batch effects if they're small, but if they're big, then you may really be dealing with an apples and oranges situation where you can only integrate the data through a technique that we call meta-analysis, which basically means that you analyze the different data sets separately without trying to normalize them onto a common frame, and then just integrate the results. So rather than integrating the data, you're integrating the results. So there's kind of a spectrum of techniques wherein if the batch effects are weak, you can actually integrate the data, and if the batch effects are strong, you analyze the different batches separately and then integrate the results. And there's actually some of the things up here on this slide that I didn't mention. The sort of more sophisticated modeling techniques like estimating equations approaches and mixed effects models and so on are particularly useful when you have data that have a more complex structure than just a bunch of individuals and their associated genomic and outcome measures. Like when they're stratified by the column that was used to deplete something, or when they're stratified by the instrument that was used or the technician or whatever. There are regression-based approaches that can go certain ways towards removing batch effects, but it seems like almost every question, my answer is that there's no silver bullet. It's very context specific.